Okay, I hope I'm audible to all the students who are attending this lecture of introductory econometrics. Okay, in the previous lectures of econometrics, we were doing linear regression. Okay, if all of you can recall, in this lecture, we intend to start with hypothesis testing within linear regression. So our agenda for this lecture is hypothesis testing, hypothesis testing two variable linear regression model. Hypothesis testing of a two variable regression model. So let's start. Before doing the hypothesis testing, let's first of all look at the basic assumptions of the classical linear regression model. We were doing the classical linear regression model in the previous lecture. If you all can recall, we had done the stochastic and non-stochastic population regression function, stochastic and non-stochastic sample regression function. Okay, we had done the properties of the sample residual terms also in the previous lecture. Okay, now in this particular lecture, let's first of all look at the assumptions of classical linear regression model. So assumptions of classical linear regression model, CLRM. So let's look at these assumptions one by one. So the first assumption is the regression model. The regression model is linear in parameters. We had done this concept of linear in parameters versus linearity in variables in our lectures on linear regression. When I say that the regression model is linear in parameters, the parameters here are B1 and B2, if you all can recall. So we say that the regression model is linear in the parameters. It may or may not be linear in variables. It may or may not be linear in variables. So I hope all students have understood the first assumption. The first assumption of classical linear regression model is that when we talk of linear regression, it is linear in parameters. The parameters are B1 and B2. It may or it may not be linear in the variables. Variables are the xi's. Okay, so I hope students are clear. So guys, we will be taking our regression as follows. Basically, in the entire lecture, we will be taking our regression as yi is equal to b1 plus b2 xi plus ui. In the entire lecture, we will be considering this simple linear regression. Yi is equal to b1 plus b2 xi plus ui. B1 is the population intercept term, B2 is the population slope coefficient. Together, B1 and B2 are called the regression parameters. UI is the population disturbance term. Okay, the second assumption of classical linear regression model, the explanatory variable, X is uncorrelated. It is uncorrelated with the disturbance term u. With the disturbance term u. Okay, so our explanatory variable, which is also the non-stochastic variable x, has no correlation with the population disturbance term u. Okay, this is our second assumption. Third assumption of classical linear regression model: given the value of xi, given the value of xi, the expected or the mean value, the expected or the mean value of the disturbance term u is 0. What does this mean, guys? This means the expected value of the disturbance term given the value x equal to xi is equal to 0. If you all can recall, we had done this particular assumption in our lectures of linear regression. We had said that the disturbance term will sometimes take positive values, sometimes it will take negative values. So on an average, the positive and the negative values will cancel out each other, so leaving the expected value of u equal to 0. So guys, it simply means for one particular value of x, remember guys, remember the basic theory. For one particular value of x, you have lot of y's and lot of u's. So for one particular value of x, u will sometimes take positive, sometimes take negative values. On an average, they cancel out. So for one particular value of x, expected value of u is equal to 0. So hoping students have understood this. Okay. And then guys, let's look at the fourth assumption. So I am erasing the three assumptions and let's talk about the fourth assumption. So assumptions are getting continued. Assumptions of classical linear regression model continue. Let's look at the fourth assumption. The variance of each UI, the variance of each UI is constant. Or if you all can recall, the term which we had used was homoscedastic. The term which we had used was homoscedastic. If you all can recall my lectures on linear regression, we had made the assumption that variance of UI will always be the same. Variance of UI is equal to sigma square, which is also called the homoscedastic variance, which is also called the homoscedastic variance. That means if you all can recall, I had drawn this diagram in my initial lectures of linear regression, if you all can recall. So we had the variable x, variable y. Okay. For every particular value of x, we have lot of values of y. Okay, if you can recall, we had drawn this diagram in the initial lectures of linear regression. And then we have the expected value of y for each of these values of x. When I join them, I get the population regression function. If you all can recall, okay. Now the variance of UI is the same, means what? It means the spread around the mean value is the same. If you look at the spread around the mean value or the expected value is the same. So we have homoscedastic variance. So if I say it in other words, the spread of the UIs from their mean value will be the same across all x's. So I hope students have understood this crucial assumption. It's a very important assumption, guys. Later in my econometrics lectures, I will be violating these assumptions. We'll see what happens if the variance is not constant. But right now in this particular lecture, the crucial assumption is that the variance of each ui is a constant. So for x1, I have u1. Variance of u1 is a constant. For x2, I have u2. Variance of u2 is also a constant, and it's the same as variance of u1. Similarly, for xm, I have um. Variance of um is also a constant, and it's equal to all the initial variances. So I can say variance of u1 is equal to variance of u2 is equal to dot 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 variance of um is equal to sigma square. I can write it like this, guys. Variance of u1 is equal to variance of u2 equal to dot 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 variance of um. All are equal to sigma square. So I hope students have understood this basic assumption of homoscedasticity. Okay. So guys, this was homoscedasticity. Suppose I show you heteroscedasticity. Heteroscedasticity means variance is changing. So this was the diagram for homoscedastic variance. This was the diagram for homoscedastic variance. You can see the spread is the same across all different values of x. Let me show you the diagram for heteroscedastic variance. So you can see on your screen, I am drawing the diagram for heteroscedasticity. Heteroscedastic variance. Heteroscedastic variance means variance is not a constant, it's changing. So you all can see the diagram. This is variable x, variable y. Okay. Again, you can see for various value, for a given value of x, you have lot of values of y. Okay. So when I join these points, I get my population regression function. Okay. So this is my population regression function. Now, guys, when I say heteroscedastic variance, you can clearly see. So you can see the spread will now change. You can see the spread will now change. See, in every case, you can see the spread is different. In diagram A, you can clearly see that the spread of the UIs around their mean value is the same across all x's. But in diagram B, what do you observe? The spread of the UIs around their mean value is changing for different values of x. That means in the second case, variance is heteroscedastic. It's not constant. Whereas in the first case, variance of UI is homoscedastic. It is constant across all different values of x. Okay, so if I write in words, what does this homoscedastic assumption mean? So this assumption of homoscedasticity means, this assumption of homoscedasticity means that the conditional distribution of each y population corresponding to the given value of x, has the same variance. This is another way of saying it, guys. One way of saying it is that variance of ui is sigma square. Another way of saying it is that for every fixed value of x, the conditional distribution of the y population That means for every fixed value of x, the deviation, the square of the deviations of the y values from their means will have the same variance. Okay, let me go over it once again so that students are crystal clear. When we talk of homoscedastic variance, it simply means for a fixed value of x, the conditional distribution of the y population will have the same variance. That means if you take the sum of the squared deviations of the y values from their means, it will come out to be the same across all values of x. Another way of saying it in simple terms, across all values of x, variance of ui's will be the same, where ui is nothing but the difference between actual y and the expected y. Ui captures how the actual y differs from the expected y. So another way of saying it would be that when we talk of homoscedastic variance, the conditional distribution of the y population will have the same variance. Okay, so let's move forward to the next assumption. Okay, fourth assumption is done. Let's talk about the fifth assumption. On your screens, the fifth assumption is that there is no correlation. There is no correlation between the two error terms. There is no correlation between the two error terms. So this means this is the assumption of, now guys, you can recall from my lectures, initial lectures of linear regression, this is the assumption of no autocorrelation. What does no autocorrelation mean? No autocorrelation means that any two disturbance terms will have no correlation. So I can say mathematically or statistically it means covariance of ui comma uj is equal to 0 for I not equal to j. When we say that there is no autocorrelation, it means any two disturbance terms ui and uj are not correlated with each other. You cannot predict any pattern between them. You cannot say that if ui is increasing, uj is also increasing, or uj is falling. You cannot predict any trend or any pattern between them. They completely share no correlation. That means another way of saying it is that the disturbance terms are completely independent of each other. Okay, so if you want to understand it diagrammatically, you can look at it diagrammatically as well. So suppose we have ui on the vertical axis and uj. Okay, so you can see I'm drawing three diagrams. You can see on your screen I'm drawing three diagrams for ui and uj. So guys, if I plot a scatter diagram. Now suppose my scatter diagram is coming like this. Suppose my scatter diagram comes out like this. You can see in this case there is no trend. We can't say that there is a pattern which is being followed. So this is the case of, this is diagram A, which is the case of no correlation. However, guys, if the scatter plot, if you plot a scatter diagram between ui and uj, if it's coming out somewhat like this, if the scatter plot between ui and uj comes out like this, then you can clearly see that there is an upward trend. When uj is increasing, ui is also increasing. So in the second case, I can say that there is positive correlation. In the second case, there is positive correlation. Okay. And the third case, if you can observe while drawing a scatter plot, if you observe a downward trend means when uj is increasing, ui is falling. If you observe a downward trend like this while plotting a scatter diagram, you say that there is negative correlation. There is negative correlation. So I hope students are clear. So the assumption of classical linear regression model is that there is no correlation. No correlation means ui and uj are completely uncorrelated. Okay, and then guys, we can write a note. Very important point to understand here is, since ui and uj are assumed to be uncorrelated, since ui and uj are assumed to be uncorrelated, it means, what does it mean? It means that any two y values will also be uncorrelated. Any two y values will also be uncorrelated. What does this mean, guys? This means covariance of yi comma yj will also be equal to 0. Now, what does this mean? Now, guys, you need to understand that the variance in y is coming because of the variance in the disturbance term. You can clearly see, I am giving you the reason. This is because yi is equal to b1 plus b2 xi plus ui. Now guys, b1 plus b2 xi is deterministic. It's fixed. Values of b1, b2 are fixed. Xi is also fixed. It's non-stochastic. So since I can write, since the b's and the x's, since the b's and the x is assumed to be fixed, since they are assumed to be fixed, y will vary as u varies, or I can say yi will vary as ui varies. So guys, if ui's are uncorrelated, then the yi's will also be uncorrelated. So guys, I am revising the fifth assumption again with all students. The fifth assumption of classical linear regression model simply states that if you take any two disturbance terms, ui and uj, where ui is not equal to uj, then they share no correlation. This simply means you cannot predict any pattern between them. So if you look at the diagram, only the first diagram is valid, where ui and uj have no correlation. In the second diagram, you can see there is a positive trend, which means there is positive correlation. In the last diagram, you can see that there is a downward trend, so there is negative correlation. And now, since our regression is yi equal to b1 plus b2 xi plus ui, and by assumption b1, b2 and xi are fixed, that means as ui varies, yi will also vary. And since we have assumed that ui's are uncorrelated and yi depends on ui, we say that yi's are also uncorrelated. Yi's are uncorrelated means covariance of yi and yj is equal to 0. Now guys, understand this. All this is happening for one fixed value of x. Okay, you need to understand this, or I can say, let me put it in a much better way. For one fixed value of x, you have lot of values of y and lot of values of u's. But when I talk about covariance of ui and uj, this is across different values of x. Because for x1, you will get u1. Or I can say for x1, u1 is a random variable. For x2, u2 is a random variable. For x3, u3 is a random variable, and so on. So when I say that covariance of ui uj is equal to 0, ui comes from xi, uj comes from xj. So the x's are different in this case. Similarly, when I talk about this yi and this yj, these are not the y's for one value of x now. These are the y's for two different values of x. Yi you get from xi, yj you get from xj. So please do not think that yi and yj are coming from one x only. No. For one, remember guys, always remember, for one fixed value of x, you have lot of values of y's and lot of values of u's. But when we are talking about covariance, when I say that covariance of ui and uj is equal to 0, it simply means that for two different values of x, for xi, I get ui, for xj, I get uj, covariance of ui and uj is equal to 0. Similarly, for xi, I get yi, for xj, I get yj, covariance of yi and yj is equal to 0. So another way of saying it, across different values of x, the ui's and the yi's are uncorrelated. They do not share any correlation. So I hope students have understood the fifth assumption as well. Let's move forward to the sixth assumption, guys. The regression model is correctly specified. Correctly specified means that all the variables which can possibly impact y have been taken into account. So another way of saying it, that there is no specification bias. There is no specification bias or error in the model used in empirical analysis. So guys, I can put it like this. What does this mean? So this assumption simply means that we have included all the variables that affect a particular phenomena. We have included all the variables that affect a particular phenomena. So hoping students have understood this assumption. When I say that the model is correctly specified, it means what? When I say that the regression model is correctly specified, it means I have taken into account all variables which can have an impact on the dependent variable. And when the model is correctly specified, it means there is no specification bias or error. There is no specification bias means what? It simply means that I have taken into account all the relevant variables. I am not adding any irrelevant variable. I am not dropping any relevant variable. Understand this, guys? Suppose I talk of demand for a commodity. When I say that the demand equation is correctly specified, it means I have taken into account all factors which can affect demand, like own price of commodity, price of related goods, substitutes, complements, income of the consumer, taste and preferences, future expectations of price. Okay, all factors which can possibly affect demand have been taken into account. And since we have taken all the relevant variables which can have an impact on the dependent variable, it means that there is no specification bias. Because remember, specification bias will occur when you are adding an irrelevant variable or when you are dropping a relevant variable. To understand more on this, kindly attend my lectures on specification bias, which will happen later. Okay, so guys, these were the 6 assumptions of classical linear regression model. First assumption, regression model is linear in parameters. It may or may not be linear in the variables. Second assumption, the xi's and the ui's are uncorrelated. Third assumption, expected value of u is equal to 0 conditional on a given value of xi. Fourth assumption, ui's have homoscedastic variance. Fifth assumption, that there is no autocorrelation between ui and uj. Okay. Sixth assumption, that the model is correctly specified. There is no specification bias. We have taken into account all variables that can affect a particular phenomenon. So hoping students have understood this. So guys, let's move forward now and let's talk about variances and standard errors of the OLS estimators. All students can recall in the previous lecture we had performed the ordinary least squares method. If you all can recall, we had minimized the sum of we had minimized summation ei square, if you all can recall, and we had chosen b1 and b2. Okay, that was the OLS procedure which we had performed in the previous lecture of linear regression. Okay, so in this lecture we look at the variances and standard errors of the OLS estimators. Okay, now guys, understand this. Now let's come to the sample, because we don't know the population. Now when I take a sample, when I take one sample and when I run a regression, I get one sample regression function. One sample regression function will give me one value of small b1 and one value of small b2. Now guys, when I take another sample and when I run a regression, I will get another value of small b1 and another value of small b2. Then I take another sample, I get another value of small b1 and small b2. That means small b1 and small b2, which are estimating capital B1 and capital B2 itself, are random variables. Understand this, guys? Small b1 and small b2, which are estimating capital B1 and capital B2 itself, are random variables. So I'm quickly writing the population regression function was yi is equal to capital B1 plus capital B2 xi plus ui. Okay, and our sample regression function was yi is equal to small b1 plus small b2 xi plus ei. Both of these are stochastic. Okay, population regression function and sample regression function. Okay, now small b1 is used to estimate capital B1. So I can write b1 is an estimator of capital B1. Small b1 is the sample intercept term. Capital B1 is the population intercept term. Small b2 is an estimator of capital B2. Small b2 is the sample slope coefficient, capital B2 is the population slope coefficient. And EI, which is my sample residual term, is an estimator of the population disturbance term UI. Okay, now guys, understand this. For one sample I have taken, I get one value of B1 and B2. If I take another sample, I get another value of B1 and B2. That means B1, B2 themselves are random variables. Okay, so, and if you all can recall, from the OLS procedure, our B2 had come out as, please refer to my previous lecture, it was covariance of xy upon variance of x. Okay, which was nothing but summation xi minus x bar into yi minus y bar upon summation xi minus x bar ka square. And what was my B1, guys? B1 was nothing but y bar minus B2 times x bar. B1 was y bar minus B2 times x bar. Now guys, B1, B2 themselves are random variables. And any random variable will have mean also, it will have variance also. So now I am presenting to all of you the variances of B1 and B2. Now understand this, B1 is estimating capital B1, B2 is estimating capital B2. You have lot of B1s, lot of B2s. So since they themselves are random variables, so I can say B1 and B2 are random variables. They will take different values for different samples. For one sample, you run the regression, you get one value of B1, B2. You keep on taking different samples, B1 and B2 will keep on changing. Okay, so what is the variance of B1? So variance of B1, which we also write as sigma square B1, is nothing but summation capital Xi square upon n times summation small xi square into sigma square. Now students should learn up this formula. If required, we will be doing the proof also later, but right now in this particular lecture, the proof is not necessary. Right now, students should know that this is the variance of B1. Small b1 is estimating capital B1. And since it's taking different values, its variance is nothing but summation capital Xi square upon n times summation small xi square into sigma square, where small xi is capital Xi minus x bar. Okay, and similarly guys, the standard error of B1 will be the square root of variance of B1. Okay, so standard error of B1 will be the square root of variance of B1. Okay, so I hope students are clear with this. Then let's talk about variance of B2. Now B2 is estimating capital B2. Its variance is denoted by sigma square B2, which is sigma square. What is sigma square, guys? The homoscedastic variance, if you all can recall. Sigma square is the variance of the UI, is the homoscedastic variance. So sigma square upon summation small xi square. Again, where small xi is nothing but capital Xi minus x bar. Small xi is nothing but capital Xi minus x bar. So hoping students have understood this. Okay, and similarly guys, what will the standard error of B2 be? Standard error of B2 will be the square root of variance of B2. Okay, in both these cases, what is sigma square? Sigma square is the homoscedastic variance. It is the variance of the disturbance terms, that is the UIs. Okay, now guys, again, sigma square denotes the variance of the population, but we don't know the population, right? Or what we know is the sample data. We don't know the population. So now what we are doing, we are trying to estimate sigma square. So I am writing for all of you what will be the estimator of sigma square. So erasing this particular part, which you already know from the previous lecture, let us now write the estimator of sigma square. Sigma square is the population homoscedastic variance. What will the estimator of sigma square will be what? So we can write the homoscedastic variance. The homoscedastic variance sigma square is estimated by using the following formula. It is estimated by using the following formula. The formula is as follows, guys. Sigma hat square is equal to summation EI square upon n minus. Now, guys, how many parameters are there, including the intercept term? We have two parameters, parameter 1, parameter 2. So n minus 2. So sigma square is the population homoscedastic variance, but we do not know the population. So an estimator of sigma square is given by sigma hat square. Sigma hat square is something which we get from the sample. This is summation EI square. Summation EI square is also called the residual sum of squares. Although we'll be taking it up for discussion later also in the lecture, but you should know summation EI square is also called the residual sum of squares, divided by n minus the number of parameters in the model, including the intercept term. Now our model is this. How many parameters we have including the intercept term? 2 parameters, so n minus 2. Okay, so I can write where sigma hat square is the estimator of sigma square. Okay, summation EI square. What is summation EI square, guys? EI itself is nothing but yi minus yi hat ka square, also called the residual sum of squares. It is the difference between the actual and the estimated y from the sample regression. Okay, and what is n minus 2? N minus 2 is nothing but my degrees of freedom. DOF, degrees of freedom. That is the number of independent observations. In simple words, guys, it's nothing but, so why are we subtracting 2? Because one observation is lost in calculating B1, another is lost in calculating B2. Since there are two parameters, capital B1 and capital B2, so we have only n minus 2 independent observations. So hoping students have understood this. Okay, so you can think of it like that, that one observation goes in calculating B1, another observation goes in calculating B2. So number of independent observations or degrees of freedom we have is n minus 2. Okay, so hoping students are clear with this. And now, guys, let's define sigma hat. So what is sigma hat? So erasing all this now. Let us now define sigma hat. So sigma hat is nothing but square root of sigma hat square. So this is known as, sigma hat is known as the standard error of regression. It is known as the standard error of regression, which we also call short form SER, standard error of regression. So what does sigma hat capture? It captures the standard deviation of the y values about the estimated regression line. Very simple. So I can write which is simply the standard deviation. It is the standard deviation of the y values about the estimated sample regression line. About the estimated sample regression line. Okay, now guys, you all need to understand something very important about sigma hat. So erasing this part, I'm erasing the population regression function and sample regression function. You know them now. Okay, very important thing about sigma hat is that sigma hat is also called or I can say sigma hat is a measure of goodness of fit. It is a measure of goodness of fit. What does this mean? It means how good your sample regression is in estimating the population will be captured by sigma hat. Now, smaller the value of sigma hat, closer the y value, or I can say for more clarity, closer the actual y value is to the estimated value y hat in the sample regression. Okay, so guys, that model which has lower sigma hat is a better model. Why? Because smaller the value of sigma hat, closer the actual y value is to the estimated y value. Obviously, guys, we would want the standard error to be as less as possible. We would want to fit our sample line in such a way so that the actual y values are closer to the y values which we have estimated from the sample regression. Basically, guys, we would want the yi's to be as close to yi hats. I repeat, we would want the yi's, which are the actual y's, to be as closer to yi hats, which are the estimated y's. Okay, so sigma hat, also called the standard error of regression, measures the goodness of fit. It means goodness of fit simply means how better your sample regression model is, how properly you have fitted the regression line for the sample. So lower value of sigma hat would mean that the actual y values are closer to the estimated y values in the sample, which means your model is better, your fit is better. However, if sigma hat is large, it means the actual y values are far away from the estimated y values, which means you have not fitted a good model. You need to recheck your data. Okay, so we would want sigma hat to be as small as possible, because lower the value of sigma hat, closer will be our actual y values to the estimated y values, which means we have fitted a good regression line. from the sample. Okay, so this is where I intend to stop in this particular lecture. Okay, what we have primarily covered in this lecture are the key assumptions of classical linear regression model. Okay, and we have looked at the variances and standard errors of the OLS estimators. The OLS procedure we had performed in the previous lecture. We had got the values of B1 and B2. In this lecture, we learned that for one sample, you get one value of B1, B2. For different samples, you get different values of B1, B2. So B1, B2 themselves are random variables. And since they themselves are random variables, they will also have variances and standard errors. So this is my variance of B1. This is my variance of B2. Standard error is nothing but the square root of variance. And this is my estimator of sigma square, which is my homoscedastic variance. And the square root of sigma hat square, which is sigma hat, is called the standard error of regression, which measures the goodness of fit. The standard error of regression, which is sigma hat, will simply capture the standard deviation of the y values about the estimated sample regression line. Lower the sigma hat, better the sample regression fitted. Higher the sigma hat, it means you need to check your data. You have not fitted a good regression line from the sample if your sigma hat is large. So guys, this is where I stop. In the next lecture of introductory econometrics, we will do a very important theorem in linear regression called the Gauss-Markov theorem. So we will be taking it up for discussion in the next lecture. So I stop in this lecture. Any doubt, you can unmute your mics and ask, or you can call up or mail me your doubts at divineschoolofeconomics@gmail.com. So this is where I stop.